Okay, welcome back, guys, to our channel. And for those persons that are visiting us for the first time, please kindly subscribe by hitting the subscribe button and as well clicking on the bell icon. Thank you very much as you do that. And for the returning subscribers, thank you very much for always coming back to watch our videos. And please do not forget at the end of the session to like and comment on the video. Okay, thank you very much. In today's class on thermodynamics, before we proceed, we'd like to talk about what thermodynamics is. Thermodynamics is a branch of physical sciences that deals with the relationship between heat and other forms of energy. It's a branch of physical science that deals with the relationship between heat and other forms of energy. Okay, so what we're going to be looking at in today's class would be terms used in thermodynamics, the terminologies made use of in thermodynamics, and of course the laws of thermodynamics. We have the first, the second, the third, and the zeroth law. We also have application of the first law and thereabout. Okay, so let's look at the terminologies that is often been made use of in thermodynamics. We have system, surrounding, boundary, and of course the universe. Okay, so like I said, a system is a definite part of the universe which is set aside from the rest of the universe for study. Okay, now for example, now if you're actually boiling water in your kettle, okay, so the system in this case is the water enclosed in that kettle. All right, the wall of the kettle is a boundary. The area outside the kettle is the surrounding. Of course, the entire kitchen can as well be seen as the universe in this case, right? Because the kitchen comprises of the kettle, the water, the outside kettle, and thereabout. So we said a system is a definite part of the universe which is set out from the rest of the universe for study. Okay, so I just did a cool explanation for that. Okay, what is surrounding? The space or part outside the thermodynamic system. It is usually restricted to the regions very close to the system. Just like I told us earlier. For example, I just like making use of kettle. If you have kettle with water inside of it, okay. So if you actually want to check out which of this is the system, the water inside the kettle is a system. The wall of the kettle is a boundary, and the outside kettle is a surrounding. Okay, we always do this to those regions very, very close to the system. Of course, you can't go ahead and say the whole kitchen is the surrounding. Okay, so it's just that specified region close to the kettle that you classified as the surrounding. Now, the boundary is the separation between the system and its surrounding. Just like I said, the wall of the kettle is a boundary because that is what separates the water inside the kettle from the outside kettle. Okay, so what is the universe? The universe is a system and its surrounding. Okay, so the system and its surrounding constitute the universe. Okay, we have types of system. The three major types of system that we have the open system, the closed system, and the isolated system. When is a system said to be open system? Of course, open system is a type of system where there is an exchange of both energy and mass across the boundary between the system and the surrounding. A typical example is let's take for example now your kettle. If you're boiling water in your kettle, remember water always kettle usually have this small orifice, this small mouth where you can pour out the water from. Okay, and that small mouth serves as an avenue where vapor can evaporate or escape from in the case the water starts boiling. Okay, so in the case of a kettle, right, when you boil water, you get to a point where the water starts boiling. If you touch the wall of the kettle, and when you finally bring it down, the wall of the kettle becomes hot. Now, for the fact that it is hot, that hotness is basically exchange of temperature between the water and the environment. All right, so eventually if you keep it for a very long time, the water gets cold. That means there is an interaction between the surrounding and the water, which is a system. Okay, so the temperature in this case is more like the energy, because if you increase temperature of a system, you increase the energy. All right, so in this case now, that kettle can exchange its temperature. The water inside the kettle can exchange its temperature with the outside temperature. Realize that at a point, the water will actually reduce in temperature and become warm, and then subsequently becomes cold. All right, so that same kettle now, when you're boiling it, the water can escape from the mouth. So this type of system where there is an exchange of both energy and mass, the energy in this case is a change of temperature. The mass in this case is the water evaporating. Okay, so in a case where there is an exchange of energy and mass across the boundary between a system and its surrounding, that kind of system is an open system. Okay, remember, energy can also be classified as temperature. Mass can also be classified as matter. Okay, so closed system, on the other hand, is a kind of a system, kind of a thermodynamic system where there is exchange of only energy and not mass. Okay, just imagine you have your pot. Your pot this time around, a pot that has a very well sealed cover, such that when you cover it, there is no way vapor will actually escape. So you realize that the water inside the pot actually will not escape easily. But then the temperature, if you touch the wall of the pot, the side becomes hot, which means there is an exchange between the system and the surrounding. So this type of system where there is exchange of only energy or temperature but not mass is called a closed system. And there is also this interesting system that we call isolated system. Okay, for example, have you ever imagined a flask that is mostly used by nursing mothers, right, to preserve hot water, right, for subsequent use in making the baby's food? Okay, so you realize that they actually boil the water and transfer it into a flask. That flask stores the water for like 2 3 days, as the case may be, depending on the authenticity of the flask. So this type of flask now can be regarded as an isolated system, because if you touch the wall of the flask, you're not going to feel any kind of hotness. That means there is no exchange of heat between the system and the surrounding. Okay, but eventually the water will get cold, because that is not an ideal isolated system. But that's the closest example that I can use to explain isolated system. The water content remains intact, the water will not reduce, as well the mass of the water remains the same, and the temperature of the water at first will not really change except with time. So these are the three major types of systems. So therefore, isolated system is a system where there is no exchange of both energy and mass across a boundary. In summary, I'll retake this all over again. Open system, there is an exchange of both energy and mass across the boundary. Closed system, there is exchange of only energy and not mass across the boundary. And isolated system, there is no exchange of both of them, right? Both the mass and the energy is not being exchanged. Okay, so since we've actually seen the terminologies that is made use of in thermodynamics, you should get yourself acquainted with these terms, because they might actually ask you in exams. Now, let's look at first law of thermodynamics. Of course, this is not the first time we've heard about this. Energy can neither be created nor destroyed, and the rest of them. So many of us will actually knew this statement even before knowing that it belongs to first law of thermodynamics. So first law of thermodynamics states that energy can neither be created nor destroyed in any physical or chemical process, but can be converted from one form to the other. Okay, it simply means that if you're actually taking food, the energy you're going to get from that food will be converted to another form of energy and expended as another form of energy. At the end of the day, you're not wasting any one of them. Okay, so first law, I repeat, first law states that energy can neither be created nor destroyed in any physical or chemical process, but can be converted from one form to the other. Now, one important factor or point that is always very, very interesting about first law of thermodynamics is that, or laws of thermodynamics, is that each of the law is actually about something. Okay, first law is about something. First law is about energy and its conservation. Okay, conservation of energy can also be referred to as first law of thermodynamics. Just like in physics, we have the law of inertia and the rest of them. So first law of thermodynamics is about energy and its conservation. For something to be conserved means at the end of the day, nothing is wasted, all right? So first law of thermodynamics is about energy and its conservation. Now, second law of thermodynamics is about spontaneous process. All right, so basically you realize that each law of thermodynamics has their unique features or properties that is kind of used to describe them. Okay, so first law of thermodynamics is about energy and its conservation. Please take note of this. It can come in your exam, as most lecturers can equally ask you this. Now, mathematically, first law of thermodynamics can be expressed as follows. First law of thermodynamics can be expressed as follows. Changing the E equals to the Q plus W. All right, this form is in a form of exact differential. You don't use this particular form to carry out calculations, but we use this particular form to carry out further derivation of formulas. When you integrate this, it's more like saying when you integrate this from position 1 to position 2, you integrate this. This is actually exact differential. This is a state function. That's why you move from state 1 to state 2. Enthalpy is a state function. That's why we're having 1 and 2. However, heat is not a state function. Hence, the reason why you're not seeing 2 and 1 here. So when you integrate this, you have change in internal energy delta E equals to Q plus W. Okay, so our delta E is change in internal energy. Delta E is change in internal energy. Delta Q rather is heat absorbed or evolved. Now, it's very, very important for us to know that this statement, absorbed or evolved, goes alongside with a sign. Okay, I believe you could remember in terms of thermochemistry, we have what we call the endothermic and exothermic. All right, so endothermic simply refers to a case where heat is absorbed, endo, so the enthalpy or the heat will be positive. Exothermic is a case where heat is evolved. So anytime heat is evolved, anytime your heat is evolved, please, delta Q is going to be negative. Anytime heat is absorbed, Q is going to be positive. All right. Okay. Now, work done by or on the system. This work done also has a sign convention. Work done by the system is negative. Work done on the system is positive. So when they say a system does work, of course, you're to add negative to whatever value that was given to you. They said work is done on the system. Of course, you add this. It's actually very important for us to state this, that work done by system is same as work done on surrounding. So when they say work done by the system, of course, if the system should do the work, it is being done on the surrounding. Just like you slap somebody now, you're the one doing the slapping and the other person is the one receiving it. It's more like a complementary action. All right, if a system is doing work, the work must be done on something, and vice versa. So if I should say work done by the system, is equivalent to saying work done on the surrounding, and the sign will remain negative. So most of the time, they might want to play very fast on students instead of saying work done by the system, because they know most students are very familiar with by the system. They'll simply say work done on the surrounding. If work is done on the surrounding, it actually means that the work was done by the system. Okay, all right. So, and vice versa. What do I mean by vice versa? They can change it to be, if work is done on the system, it will be by the surrounding. Okay, please take note of that. All right. So let me actually write it out here so that I'm supposed to clean this. Okay, so just make this point so that I'll say note work done by system equals to work done on surrounding. the sign is always negative. Also, or similarly, work done on system is equivalent to work done by surrounding. So if I have this, if I have okay, so if I have work done by the system, anytime they say work done by the system is equivalent to saying work done on the surrounding, just like I explained previously that if I particularly should slap somebody, all right, I'm slapping the person. It's more like a complementary action. If I'm slapping somebody, of course, I'm the one doing the slapping, so the slap is done by me and is on somebody. Now, if you reverse it, if that person is doing the one, if the person is the one slapping me, it will be on me. So work done by the system is equivalent to saying work done on the surrounding. The sign is always negative. So please watch out for this. They might say work done by the system is the same thing as saying work done on the surrounding. And work done on the system is by the surrounding and vice versa. Okay, let's make progress. We have a question here to actually tackle, right? We want to actually carry out calculations with regards to the first law of thermodynamics. An electric motor does a 200 kilojoules of work driving a belt, all right, and loses 35 kilojoules as heat in the process. What is the change in the internal energy of the electric motor? Now, how would I know that this particular question, I will use first law of thermodynamics? You look at the parameters that is being given to us in this question. All right, they told us that electric motor does 200 kilojoules of work. The electric motor in this case is assumed to be the system because it is the one doing the job. All right, so electric motor does 200 kilojoules of work. They have given us work W to be 200 while driving a belt, and in the process the belt loses 35 kilojoules as heat. So that means they have given us Q, and you're asked to solve change in internal energy. Now you ask yourself, what is the relationship between change in internal energy with work and heat? Of course, it is the first law of thermodynamics. All right, now look at this. The question mark here simply means that change in internal energy, which is delta E, is what I'm looking for. W here is the work done, which they gave me to be 200. This negative sign here was not indicated in the question, but they made a statement that you're supposed to use to actually fix up the negative sign. They said an electric motor does a 200 kilojoules of work. That simply means that electric motor in this case is a system and work is done by the system, and work done by the system is negative. So that is why I added negative here. So I said the negative sign is because work is done by the system. Remember, anytime the system does work, it is negative. And the system in this case is the electric motor. Okay, the negative because now this Q here, they give us heat. The Q is always heat absorbed or evolved. All right, so when something loses heat, evolution of heat means loss of heat. Absorption of heat means gain of heat. So when they told us that the system loses 35 kilojoules of work, it means heat was evolved, heat was given out. And the sign convention for evolution is negative. So we're going to add negative sign here to show that heat was given out. So the 35 kilojoules, we'll write it down. Now, if you notice the 2 units of this, they are in kilojoules. They are in kilojoules. All right? So there is no need of converting them. Assuming one of them was in joules and the other was in kilojoules, there will be need for us to actually make sure that the units are uniform. But since in this case this is kilojoules and this is kilojoules, of course we proceed like that. So using first law of thermodynamics, delta E equals to Q plus W. Okay, our Q here was minus 35 kilojoules. So I put down minus 35 kilojoules plus our work done here is minus 200 kilojoules. So I insert minus 200 kilojoules here. When I carry out this evaluation or the simplification, we have minus 235 kilojoules as the change in internal energy. Alright, what if in a case where you were asked to present your answer in joules? If you're asked to present your answer in joules, it's very simple. You multiply this by 1000. So this is going to be minus 235,000 joules. That is if you were asked to present your answer in joules. Okay, so let's look at the next question here. The next question said, calculate the change in internal energy of the system for a process in which the system absorbs 140 joules of heat from the surrounding and does 85 joules of work on the surrounding. Now, they told us that the process in which the system absorbs 140 joules of heat, that means our heat is going to be plus because heat is absorbed, gain of heat, right, from the surrounding, and does 85 joules of work. So this time around, the system is still the one doing the work because it said and does. All right, so the system is the one doing the work. So once again, it is work done by the system, and work done by the system is negative. So we put down negative here, minus 85 joules. And once again, they're asking us to solve for change in internal energy. Okay, so using first law of thermodynamics, we say delta E equals to Q plus W. Our Q here is 140 joules positive. I could equally disregard the plus. It's still the same thing, but if it is minus, I will not disregard it. So this is our Q is 140 joules plus, open bracket, our W is minus 85 joules. So 140 minus 85 is 55 joules. So change in internal energy is plus 55 joules. Okay, so let's look at the next question. They said calculate the heat. This time around, they're asking us to solve for the heat, the Q, no longer the delta E. Calculate the heat liberated when the work done to compress a gas is 9.6 times 10 raised to the power minus 2 kilojoules, and the change in internal energy of the gas is 56.2. Now we write down the parameters. We say delta E is 56.2 joules. Q is what we are asked to find. Now work done. If you notice, I gave this work done a sign, positive sign. Why is it so? Because they say compression of gas. If a gas is being compressed, that means you're reducing the volume. Do you understand? If a gas is expanding, that means the gas is actually increasing its volume. And what is going to make the gas to increase its volume is the gas itself expanding. So in this case, expansion of gas is work done by the system, because if the gas is the one expanding, it is the one doing the job for himself. But if you're compressing a gas, something is used to compress a gas. So compression of gas is work done on the gas. Something outside the system is what is being used, or the factor that is being made use of to compress the gas. So please take note that compression of gas is work done on the system. The system is a gas, and you're forcing the gas to take a smaller volume as compared to what it was initially. So that means you're forcing the gas to go against its will. All right, so that is compression of gas. Compression means work done on the system, hence the sign is positive here. Okay, so but remember I told us that for us to carry out the calculation, the two units must be the same. They gave us this to be in kilojoules and the internal energy to be in joules. We cannot carry out evaluation, subtraction, or addition when the two units are not the same. So we needed to take back these kilojoules to joules. Why didn't we take the kilojoules to the joules to kilojoules? Because joules is a unit of energy. Kilo is more like a prefix that add up to the joules. So we take back the except the question you were asked to present your answer in kilojoules. But in a case where it was not stated, it is best you take the kilojoules to joules. So for us to take the kilojoules to joules, we multiplied, or we're going to multiply by 1000. When you multiply this by 1000, you're going to get this. Okay. All right. So from delta E equals to Q plus W, right? When you make Q subject of the formula, it's more like saying delta E equals to Q plus W. You keep this one constant and take this one to this other side. This becomes QE minus W equals to Q. So we're changing E minus W equals to Q, right? Why is this place minus? Because when this positive from this side comes over to this side, it becomes negative. Okay, so that is that for this. So when our Q becomes delta E minus W, what is delta E? 56.2 joules minus W is 89.6 joules. So when you subtract this from this, you're going to have this. The sign is very, very important because it corresponds to this. They said liberated. Liberated means giving out. All right. So the heat apparently is going out, hence corresponds to this negative sign here. Okay. So let's look at application. We are done with first law of thermodynamics, the calculation. Now let's look at application of first law of thermodynamics. All right. The first application of first law of thermodynamics is pressure volume kind of work. So maybe imagine somebody asking you now, hey, could you please tell me the type of work done that is actually found in thermodynamics? Is it force times distance? In physics, the work done is force times distance, but in thermodynamics, the work done is pressure volume type of work. Right, so take note of that. Work done in thermodynamics is a pressure volume type of work. Work done in physics is force times distance kind of work. So in thermodynamics, we're looking at the pressure volume type of work. So work done here is minus P, change in V. Change in V is V2 minus V1. Okay, where our P is a pressure, V2 is a final volume, V1 is initial volume. Now the negative sign indicates that work was done by the system on the surrounding. This negative sign is always constant anytime you're carrying out this calculation. Okay, so let's look at this question. They said, what is the amount of work done when, how would you know this question is different from the other one? Based on the parameters. Now let's check this out. What is the amount of work done? You're asked to find the work done here, W, when a 200 liters of gas expands to a volume of 350. All right, you're asked to find W, and of course they gave us the first volume 200 and they gave us the second volume 350. Right, against an external pressure of 0.1 atm. So they gave us pressure of 0.1 atm at constant temperature. Okay, I repeat again, what is the amount of work done? That is, the W is what we are asked to find here. What is the amount of work done when a 200 liters of gas expands to a volume of 350 liters against an external pressure of 0.1 atm at a constant temperature? All right, so putting out the parameters, we have pressure is 0.1 atm, final volume is 350 liters, initial volume is 200 liters. So if you look at these parameters, of course, if you check out, they're asked to find work done. They gave us this. So the best formula to make use of in this case, we say work done is question mark. All right, so we say work done will be minus P change in V, which is minus P V2 minus V1. Okay, so we proceed with the calculation here. We say work done is equals to negative P, open bracket, V2 minus V1. Now the negative is constant. You retain the negative. Our P is 0.1 atm, open your bracket, V2 is 350 minus V1 is 200, you close the bracket, liters. All right, so this is 0.1 atm times 150, and this is minus 15 atm liters. Okay, so the next thing we are going to do here is to convert 15 atm liters to joules. right? You're going to convert this to joules. And for you to convert this to joules, you have to actually try to know. Now, why are we converting this to joules? Because if you keep your final answer here, it will not count. The unit of work is always in joules, same as unit of energy. So you cannot afford to leave your final answer in a unit other than joules for a work. All right. So we have to convert the ATM liters to joules. And luckily enough for us, there is a direct relationship between ATM liters and joules. All right. So it's basically, I don't know if you're following up with what we are discussing here. It's very, very important that you follow up. Okay, so this relationship, there's meant to be a point here. All right, so please effect that 1 ATM liters is equals to 101.325 joules, not 101.325. Okay, so 1 ATM liters is 101.325 joules. Please do not forget that this liters is the same thing as dm cube. All right, so they can equally say 1 ATM dm cube is still the same thing. It's still equivalent to 101.325 joules. Okay, so you carry out our conversion. We say 1 ATM liters times, I put this cancels this, leaving me with joules on top. All right, so when you now carry out this evaluation, you now have this. If you don't want to go with this, you can simply say, but this is the best conversion factor. You put 15 ATM liters, put your multiplication sign, you draw a line. You're coming from ATM liters to joules. You put ATM liters down and put joules up. And now ask yourself, what is the relationship between ATM liters and joules? You know fully well that 1 ATM liters is equivalent to 101.325 joules. So when you press your calculator, you're going to have this as the final answer. So that is the answer we're going to get for the question that were asked previously. Okay, so let's look at the next question here. We are asked a hydrogen gas cylinder at constant temperature of 25 degrees Celsius expands from initial volume of 37 liters to a final volume of 84 liters. What is the work done if the gas expands A against the vacuum, B against the constant pressure of 1645 torr? First, let's ask ourselves this question. Now, a hydrogen gas cylinder at constant temperature of 25 degrees Celsius expands from initial volume of 37 liters to a final volume of 84 liters. All right, so what we are simply going to do here basically is going to be A against the vacuum. So let's put out our parameter first. We want to get the pressure because they say we should calculate the work done against the vacuum. And of course, the work done in this case is negative P change in V. We need to know the value for P. All right, but since they said against a vacuum, it's important for us to know that in a vacuum there is no air. Okay, vacuum, there is no air, there is no force of gravity. As such, there will be no pressure. So in a vacuum, external pressure would be equal to 0. Okay, so that is why we have P to be equal to 0 here. Our initial volume is 37 liters. Final volume is 84 liters. All right, so if you actually apply this formula, W equals to minus P change in V, which boils down to this. Our P is 0, so anywhere we see P, we put 0. Why are we putting up 0 here? Because we're told that this expansion was carried out against a vacuum, so there is no pressure in there. So if there is no pressure, there'll be no work. So the volume is whatever you have here times 0 is 0. So against a vacuum, work done is 0. So take note of this. Anytime you're asked to carry out a work done against a vacuum, it is important for us to know that against a vacuum there is no pressure. As such, there will be no work done. Okay, so let's look at against a constant pressure of 1645 torr. You know, one important stuff here is that we just need to we have to convert this torr to ATM. Why are we doing this? Because there is a relationship to convert ATM liters to joules. Right? If we actually proceed with this torr, we cannot leave our final answer as pressure, because for work done, the answer must have a unit of joules. And we know that the relationship between joules and ATM liters is known. So this pressure that is given to us in torr, we need to convert it to ATM before we proceed with our calculation. Okay, once again, why are we doing this conversion? I want us to really understand why. Because there is a relationship between 1 ATM liters with joules. What is the relationship? 1 ATM liters is equals to 101.325 joules. So since this ATM liters already has a relationship between this, it is best we convert this torr to liters. Assuming this relationship was 1 torr liters, there will be no need for us to convert this. We're just going to go ahead and solve it like that. But since there is no relationship between torr liters with joules, hence we just need to convert to ATM. Okay, so for us to convert to ATM, we say 1645 torr. We put this. Now you put torr down so that this can cancel this, and you leave ATM up. You now ask yourself, what is the relationship between ATM and torr? Class, 1 ATM is equivalent to 760 torr. Okay, so when this cancels out with this, we have 1645 divided by 760, that is 2.164 ATM. So that is the equivalent of 1645 torr to ATM. So our pressure now becomes 2.164 ATM. Our V2 initially, which is final, is 84 liters. The initial volume is 37 liters. So when you insert this into this formula, work done is equals to minus P V2 minus V1. So this is minus, our P here is 2.164 ATM times V2 is 84 minus V1 is 37 liters. Okay, 84 minus 37 is 47. 47 times this will give us minus 101.708 ATM liters. But remember what I told us earlier, that you cannot leave your final answer in unit of ATM liters. Your final answer must be in joules. Okay, so we have to convert to joules. So converting to joules, we say minus 101.708 ATM liters times, you put ATM liters down and put joules up so that this can cancel this, leaving us with this multiplied with this. Alright, so we're going to say 101.325 times 101.708. Put a negative sign. So this becomes the answer. I hope you actually understand. Please, if you have any question, do well to drop a comment. Of course, I will actually respond to all of them. Okay, please endeavor to subscribe so that the continuation of this video you will not have to miss out. So please kindly subscribe, share the video to your friends. You know, of course, we need this in preparations of the exams. And please do not forget to like and comment. Once again, please, thank you. Kindly share the video and subscribe.